इस चैनल को बनाने का मेरा एक ही मकसद रहा है कि जो इलेक्ट्रिकल इंजीनियरिंग ब्रांच के स्टूडेंट्स हैं, इस स्ट्रीम के जो स्टूडेंट्स हैं, उनके जो भी डाउट्स रहते हैं 3rd सेमेस्टर से लेकर 8th सेमेस्टर तक, वो सारे के सारे डाउट्स मैं अपने इस लेक्चर सीरीज के थ्रू सॉल्व। हेलो माय डियर फ्रेंड्स, so this is the first lecture of my channel Electrical Engineering Classes, the Concept Builder, and this is going to be a 15-minute session, a 15-minute concept. So today we are going to start with the theory of transformer voltage regulation. Okay, so the topics that we are going to cover in these 15 minutes are formal definition of voltage regulation, formula of voltage regulation, conditions under which voltage regulation is being calculated, categorization of electrical load and phasor diagram of load current, phasor form of load current for various loads, derivation of voltage regulation using approximate equivalent circuit of transformer, drawing phasor diagrams and derivation of voltage regulation for lagging, leading and unity power factor loads, and the last topic for these 15 minutes will be condition for zero and maximum voltage regulation. So let's begin with our first topic. First of all, let me define what is voltage regulation in a formal way. Now, voltage regulation of a transformer is defined as the arithmetical difference. First of all, you have to note that this is the arithmetical difference. Arithmetical difference, the word arithmetical here means is magnitude. What do I mean by arithmetical is magnitude, the change in magnitude. Okay, the change in magnitude. Okay, so I have in bracket, I have written it specifically, that change in the secondary terminal voltage. Now we are talking about the terminal voltage. What is terminal voltage? The load end of the secondary. Now this is called as the terminal voltage V2. Okay, this is called as secondary terminal voltage. This is called as the secondary terminal voltage. Okay, when the load is thrown off, the secondary current I2 is going to be 0 while the transformer was working at full load. Now before throwing off the load to 0, removing the load, making I2 equal to 0, the transformer was working at full load. So we have the condition I2 is equal to I2 full load, which is also called as the rated current at a given or specified power factor of the load. Now we have connected this load here, so this load has got a specified power factor, keeping the primary voltage same for both full load and no load condition. Now in both the conditions, whether it is the no load condition or the full load condition, the primary voltage, which is V1 here, this is going to remain the same. This is the foremost definition which we must remember when we start studying the concept of voltage regulation, that we are dealing with two conditions here. First condition is the full load condition and the second condition is the no load condition. This is the condition for current. Okay, now in this diagram you can see that the transformer is assumed to be working at full load, and in the second diagram you can see that I have removed the load, so the transformer is presently working at no load. Now due to no load condition, this is going to be represented as I2 is equal to 0, and in this case the secondary current which is flowing is going to be I2 full load. So this was the formal definition of voltage regulation. The most important condition we have to remember is that the magnitude of the primary voltage, is going to remain as same. Now the second concept we are going to see is the formula of voltage regulation. What is the formula of voltage regulation? This brings a lot of confusion while studying this topic. So let me clear this concept, that the formula of voltage regulation at full load, we are studying the voltage regulation formula at full load. So the per unit voltage regulation at full load is, now I have told you that we are talking about the magnitude condition. So let me apply the mod on all the voltages that we are looking at. So voltage regulation is equal to, this is per unit voltage regulation, is equal to V2 no load, magnitude of the secondary voltage of the terminal voltage at no load minus the terminal voltage at full load divided by V2 full load. Now one condition that I just told you in the previous slide, that V1, mod of V1, that is the magnitude of the primary voltage, must remain as constant. This must remain as constant. So in percentage we are going to write it as, again I have to write that same condition, V1 is equal to constant. I hope you are writing it with me. Okay, I hope you are writing it with me that V1 is going to be constant. Now what is full load? V2 full load. V2 full load is the rated or the full load secondary terminal voltage at full load condition. At full load condition. And V2 no load is the no load secondary terminal voltage. Now points to ponder. This is the important thing that I want to tell you is now the current flowing is full load current at a given power factor. Now the current which is flowing at the secondary is full load current at a given power factor. Okay, now the primary voltage, you see I have written it as mod V1. This mod V1 represents that the magnitude of the primary voltage is going to remain same both in the condition of rated load as well as at no load. The quantities in this formula, as we see, I have written specifically V2 full load is equal to modulus of V2 full load, and V2 no load is going to be the magnitude of V2 no load. So we are only using the magnitude values only to derive the formula and to get the values. We are not interested in any kind of phasor values. I hope you are getting my point. These are not phasors. These are mere magnitudes which we are talking about. So the condition under which voltage regulation is calculated. Now we are looking at the condition at which the voltage regulation is being calculated. Rated voltage, current and frequency, it has to be rated. The load is considered to be a rated load if no hint is given about what load is given in the question data. The voltage waveforms are assumed to be sinusoidal until it is stated. If the load power factor or the power factor of the load is mentioned, then it's good and helpful, but if it is not mentioned, then we are going to use it as unity power factor. Now we are going to talk about three kinds of loads. Now my fourth topic is categorization of electrical loads and phasor form of load current. You see we have three kinds of loads: lagging, leading and unity power factor load. Now the phasor form of the load current, when we talk about lagging load, is I2. The dark colored letters represent the phasor form. I2 is equal to angle minus theta 2, which is written in this format as cos theta 2 minus j sin theta 2. Now the leading load I2 is equal to I2 angle theta 2 is equal to I2 cos theta 2 plus j sin theta 2, and unity power factor we are representing it with the help of zero angle. Now the next topic which we are looking at, we have to derive this is the approximate voltage regulation, approximate equivalent circuit, and we have referred everything to the primary side. When we have referred everything to the primary side, this voltage is going to be written as AV2. Okay, this is going to be written as AV2 and this is going to be written as V1. So the formula changes to V1 minus AV2 divided by AV2. Now what is V1 here? V1 is going to be the voltage at no load. When we remove this, we are going to get V1 as the voltage at no load. I have written the magnitude only. Okay, and the V2 is the full load voltage which is written as AV2 angle 0 degree. Why we are writing it as angle 0 degree? Because while drawing the phasor diagram, we are going to consider V2 as the reference phasor, and I2 can be this. We are not aware of the load, what kind of load we have applied here. So I have written it as I2 angle theta plus minus theta 2 or 0 for unity power factor load, and I2 has I2 we are shifting it. Now this is being shifted to this side as we have referred everything to the primary side. So this is going to be I2 dash equal to I2 upon A. I hope you are getting my point. This condition relates when we are not aware what is the value of V1. Now another slide also tells us about the same thing that we had seen in the last slide, but in this case the primary side is being referred to the secondary side. So this is going to be V2 and this is going to be V1 upon A. This time this current is going to be I2. Okay, this current is going to be I2. So now V2 no load is if we remove this load, then we are going to get as V1 upon A being shifted to the secondary side. The current I2 will have some angle, mod of I2 angle plus minus theta 2. We are not aware of the angle, and if V1 is unknown, if V1 is not known to us, then we are going to calculate V1. Okay, and how we are going to get V1 as V1 dash? This is V1 dash is equal to V1 upon A is equal to V2 plus I2. In the brackets, this is the equivalent resistance R equivalent to, which is R equivalent 1 R1 N2 by N1 square plus R2. Okay, we are going to use the equivalent values, and this is going to be the formula V1 upon A minus V2 upon V2A. Now the detailed derivation is going to be come up in the subsequent lectures or the episode classes. Okay. In the next topic, I have drawn the phasor diagram of lagging load. This is going to be theta 2 lagging load. Okay, and this is going to be del. These are both electrical angles. We are using the approximate equivalent circuit referred to the secondary side. Okay, now the formula is V1A minus V2 upon V2, I2 Re2 cos theta 2 plus I2 Xe2 sin theta 2. This is the formula we see when we are talking about a lagging load. Now you see that Xe2 has 2 pi f Le2. This means there is a term of frequency involved here. So this means voltage regulation depends upon frequency. Cos theta 2 is the load power factor, and theta 2 is the electrical angle, and V2 full load is going to be V2. We are using this V2 as the reference angle. In the leading load condition, this is going to be theta 2. You see the load current leads the secondary voltage, the secondary terminal voltage. The formula is again going to be V1A minus V2 upon V2A. Now this time we are using a negative sign. The derivation is going to come up in the next lecture. I2 Xe2 sin theta 2 divided by V2. V2 is the full load voltage. Again, it is used as the reference phasor, and it is dependent on frequency, and cos theta 2 is the load power factor, and all the angles which we are seeing are electrical angles. So in the voltage regulation of unity power factor, in the unity power factor case, the current is going to have an angle 0 degrees. So it is written in this form. V2 we are already using as a reference phasor. So if I solve it and put it in this condition, then I am going to get this in order to calculate the magnitude and minus V2. But the same thing can be calculated using the lagging power factor condition. If I put cos theta 2 equal to 0 degree, which gives me 1, and sin theta 2 is equal to 0 degree, which gives me 0, and we are going to get the same result as I have written here. So what is the condition for maximum voltage regulation? The condition for maximum voltage regulation is the condition for maximum voltage regulation. We are looking at point A. At lagging load, maximum voltage regulation occurs. The power factor is equal to the power factor, as you can see, cos theta 2 in the above equation shows that maximum voltage regulation occurs when load power factor, this is the load power factor, has the same value as angle equivalent of impedance. So this is the angle equivalent of impedance. If I draw the angle equivalent of impedance, this is going to Re2, this is going to be Xe2, X equivalent 2, and this is going to Z equivalent 2. So this is nothing but Re2 divided by Z equivalent 2. So this is the condition that you have to remember for maximum voltage regulation. Now the condition for zero voltage regulation. Now the condition for zero voltage regulation occurs in case of capacitive load. Okay, zero voltage regulation occurs at capacitive load, that is leading power factor load. Tan theta 2 when becomes equal to Re2 divided by Xe2. This is the condition that we have to remember while talking about zero voltage regulation. When theta 2 is larger than that given by the above equation, if theta 2 is larger then the condition that we are dealing here, then the voltage regulation becomes negative. Now how voltage regulation becomes negative? If the V2 no load minus V2 full load, you see how will it become negative? If V2 full load is greater than V2 no load, then definitely this is going to be negative voltage regulation. So the condition for zero voltage regulation is that the load connected to the secondary side should be capacitive or leading power factor load. For maximum voltage regulation, the load has to be lagging power factor load, and the condition is we are going to get a positive voltage regulation, V2 full load minus V2 no load. So if this becomes a positive value, that is V2 no load is greater than V2 full load, then this we are going to get a positive value. This means we are talking about the lagging power factor load in this condition. I hope the lecture was quite simple and quite easy, and detailed lecture is going to come up in the next session. I hope all the points were cleared by me, and in the next lecture we are going to get the detailed clarification about everything. But this was just to make you remember things, just to revise what we have studied in the last topics. I hope it is clear to you. All the seven topics, all the seven topics were quite simple and were totally related to the voltage regulation of the transformer. Detailed topics, if we are going to do the detailed topics, it definitely needs time, but as due to the exam constraint, I am just taking up small lectures of just 15 minutes to clear the concepts. I hope